Welcome folks, this is a new tutorial to show you how to solve for Thevenin equivalent circuit, and in this tutorial we're going to have a very simple example. So let's get started. So here we have a very simple circuit like the one shown here in this particular circuit, and then we are asking you to find Thevenin and Thevenin. Now the first thing you want to look at when you look at the circuit is you want to see that this circuit doesn't have any dependent sources, which is a relief for us when it comes to solving for R equivalent. So we know that when you wanted to find the Thevenin equivalent of this particular network, there is two steps you need to have. The first thing is you need to solve for Thevenin. The second one, you need to solve for Thevenin. So we're going to start with finding Thevenin, and to find Thevenin, basically we are interested in the voltage across the open circuit terminal at the output, which we call VOC. Now to solve for VOC in the circuit, we have to apply some critical thinking to begin with. The first thing, when I look into the circuit, that I'm going to know that the current through this resistor is going to be 0, because this resistor is open circuit. There is no path for the current to flow. That means that the current through this resistor is 0. That means the voltage across this resistor, the 10 ohm resistor, is also going to be 0. This is by Ohm's law. V equals I times R. If I is 0, then the voltage across this resistor is 0. Then if I apply KVL here, by applying KVL here, I know that the voltage across this current source is the same as the voltage across the load. Then I can say that this is VOC. Right? By applying KVL here, you're going to say that minus VOC plus 0 plus VOC equals 0, which implies that this voltage and this voltage is the same. So basically we need to solve for the voltage across this current source. Now what you end up with here is what we call a single loop circuit. Because this resistor is open circuit, it's almost like it's disappearing, it doesn't exist. That means we have a single loop circuit. Usually in a single loop circuit, the objective is to solve for the current within the loop. And clearly that the current within the loop is given to us to be 1 amp. So you would expect that the current going through R1 to be 1 amp, as shown here, because if you sum the currents at this node, you're going to have 1 current going in and you have 0 current going out. That means 1 current also leaving. So this current and that current are equal because this current is 0. So if this is 1 amp, then we know what's the voltage across this resistor. The voltage across this resistor is going to be 15 volts, is 1 times 15. And I know the voltage across the voltage source, which is 25 volts. So by applying KVL here, I will be able to solve for VOC. Now the trick is that whenever you want to solve for circuits, any kind of circuit, you have to develop a strategy before you jump into finding the solution. And the strategy is basically based on the analysis I just showed you here. So you need to develop that strategy before you solve for the circuit. Now we can state that by KVL, we're going to sum the voltages around this loop. So I'm going to use the conventional way of doing it. So if I enter the minus polarity, I will subtract. If I enter the plus polarity, I will add. So I will say that minus 25 volts, because the current through this resistor is going this way, the plus polarity is going to be over here, right? Because the current is going from left to right and the plus is going to be at the left. So I will say plus 1 amp times 15 ohms, right? That's correspond for 15 volts, right? Then I'm going to add this voltage. I'll say plus VOC. That's the end of the loop equals 0. So this is the equation that we have to solve for VOC. Then basically it's one equation, one unknown. VOC equals 10 volts. So we solved the first part of the problem, which is the Thevenin equivalent. But we know that the open circuit voltage is the same as Thevenin equivalent. We are after the Thevenin equivalent. Then we can state that Thevenin is the same as VOC, which is the same as 10 volts. So this is the first thing we asked you to solve for, which is Thevenin. Now you need to solve for Thevenin. So finding Thevenin requires us to choose the easiest technique to do that, and the easiest technique going to be R equivalent. Why we're going to use R equivalent? Because if you look into this network doesn't have any dependent sources. So if you don't have any dependent sources in your circuit, go ahead and find the R equivalent method. So the idea is to redraw the circuit after you suppressing all the voltages, and I recommend you to redraw the circuit to eliminate any kind of errors or mistakes while you are solving for the problem. So if this is your network, then you're gonna basically short circuit the voltage source, so the voltage source becomes short circuit. That's how you suppress the voltage source, and then this current source is gonna be open circuit. Right? So the idea is that if you make this voltage source 0, it becomes short circuit. If you make this current source 0, it becomes open circuit. The current through the open circuit is 0, and the voltage across the short circuit is 0. By doing that, then what you're going to do is you need to find R equivalent looking back. R equivalent looking back is basically R Thevenin. So the Thevenin equivalent will be R equivalent looking back. Clearly that this is a very simple circuit. You're going to have R2 is in series with R1. The same current will flow through the circuit. That means R Thevenin is the same as R equivalent, and in this case going to be 25 ohms, the 10 ohms plus the 15 ohms. Now this is very simple circuit, and you can find the equivalent circuit very easily, but to make the circuit more interesting, now what we're going to do is we're going to find R Thevenin using the short circuit method. So you don't have to do that. One of the two techniques to find R Thevenin will be sufficient, but here I wanted to do the extra method, which is the short circuit method, to show you the short circuit method can be sometimes the longer method. So let's redraw the circuit again, right? So this is our original network, and now I'm going to apply the short circuit method. So I have to come to the terminal AB, and I'm going to short circuit the terminal AB. And now you have a new circuit. This circuit is totally new because the load here is open circuit, but the load here is short circuit. That means those two circuits are different. They aren't the same, they look the same, but they aren't the same. Actually, they are two different circuits. Now if you look into the circuit, you are after solving I short circuit to find R Thevenin. So now the circuit will have two meshes. There is a mesh here and there is a mesh here. So we can basically say that we're gonna have two meshes. I have I1 and I have I short circuit. I called it I short circuit here because it's the same current flowing through the short circuit. So this particular circuit also has a current source between the two meshes, and because it has a current source between the two meshes, I have to have a super mesh equation. So we have two super mesh equations to represent the circuit. So the first one we will use is we will sum the voltages around this super mesh, the outer mesh, basically the combination of those two meshes, and we know that the current through R1 going to be I1, the current through R2 going to be I short circuit. So to sum the voltages around the super mesh, we know that we're going to have 15 times I1 plus 10 times I short circuit, and then we still have the 25 volts, so we're going to say that this will equal to 25 volts. This is the first equation of the super mesh. The second equation of the super mesh is basically states that the algebraic sum of those two currents will equal to this current source. So I1 will go down and I short circuit will go up. So we can say that I1 minus I short circuit equal 1. I1 is coming down minus I short circuit will equal to this current source, which is I1. Those two equations are the super mesh equations that used to represent the circuit. Now you have two equations, two unknowns, so you can solve for I1 and I short circuit. So what we end up with is I1 will equal to 1.4 amps and I short circuit will equal to 0.4 amps. So we end up solving for the short circuit current. As this is the end of the story? Not quite. We still wanted to solve for R Thevenin. So R Thevenin is basically defined as V Thevenin over I short circuit, or V open circuit over I short circuit. I already solved for the V open circuit, which is the same as V Thevenin, to be 10 volts, and I just solved for I short circuit to be 0.4 amps. And now we say that 10 over 0.4 give us 25 ohms. So clearly that we end up with the same Thevenin equivalent resistance as the one that is used here. Now you can see that using R equivalent method was much easier than using the short circuit method. I did this example just to show you that if you have no dependent sources in your network, just go ahead and find R Thevenin. Basically find R Thevenin by finding R equivalent across the terminals AB once you suppress all the independent sources. It's a very powerful technique. It is easier to use, and that's what I recommend you to do. So I hope you enjoy this video, and I will also show you another video to simulate the circuit using BSpice to show you what's VOC is and what's R Thevenin is using ORCAD BSpice. And finally, I would say that I hope you enjoyed this video and you learned from it, and good luck to you. Thank you.